So, hi everyone. So welcome back to the third day, I believe, for the 33rd Chris Engelbrecht Summer School. So this morning we have a new speaker. So we have Dr. Menica Dibenedetto. So she'll give us a lecture on quantum artificial intelligence. So just to give a bit of background. So she's a assistant professor at Maastricht University in the Netherlands, and she leads a quantum a group on focusing on quantum computing research. So yeah, let me hand over to you.
Thank you, Graham. Can you hear me a bit? No, but anyway, you can hear it also without microphone. Maybe it's for you. Okay. Yeah. So good morning, everybody. Today I will give you this lecture on quantum artificial intelligence. My name is Menica, as Graham said, and I work as assistant professor in Maastricht University. And for any kind of information that you would like to have after the lecture or material or whatever, you can contact me to this email. Okay. So a little bit of info about this lecture. So today we will talk about quantum artificial intelligence, and the next lecture will be on Sunday. Sorry that you will be here on Sunday, but yeah, we have an appointment on Sunday. I would like to work together with you. So I know that the audience is mixed. We have lecturers and where students lecture are also welcome to join if they feel like. And I would like to give you a kind of homework to do that I will describe at the end of the lecture. So on Sunday, I will ask you to divide in 4 groups, and each of the groups will give me a small pitch. So we will have 4 presentations, okay? Are you agree with this or not? Yeah. Okay. So before to start, I really would like to know who are you, because I didn't have the chance to talk with you, so I don't know your backgrounds. So you can join this book club thing. Sorry. Yeah, I just need to maybe you can scan the QR code. Okay, are you there? Everybody's in? Okay, so I will start with the question, but actually, if I go on, everything is shared, everything on my laptop is shared, right? So I cannot really just go with the question like this. Okay. Oh. Okay, so some of you already had a course in quantum computing and quantum machine learning. Okay, so everybody did. So you can be here and give the lecture then. Dennis? No? Okay. Okay, now it's more like, okay, it's a competition between. Yeah, so the majority already hear about that, right? So this is the point, more or less. And the second question is, what do you expect to learn from this lecture? So I can maybe, not yes, why yes? You always answer yes, right? I think, did I put it that you can write or not? No. algorithm, concept, game, hoping, insight. Everything about how to prompt AI, application of quantum AI. Okay, more or less we can say that we are, let's say, on the same page. Unfortunately, this lecture will not be practical, but I think if you really would like to know about quantum AI, quantum machine learning, you need to put your hands on. So if I would have more time, then I would give some exercise to do or some coding exercise. We are not going to talk about quantum algorithms. We are going to talk about quantum AI and a little bit give you the framework around it. Okay? So I hope you will not be disappointed. So the source of this lecture is basically the book from Francesco and Maria Schur, that's Machine Learning with Quantum Computer. I think I did my research. I think it's one of the book that give you a kind of overview of what is quantum machine learning. But I also would like to suggest you this other book, Quantum Artificial Intelligence with Qiskit, because there is a lot of pseudocodes. So if you really would like to understand the algorithm behind and code by your own and try to put your hands on, I think it's a nice book to practice. And then another reference that you can use is Quantum Machine Learning from Claudio Conti, which gives more a kind of neural network approach to quantum machine learning. And of course, there are a lot of papers that I will cite during the lecture that you can look at. So what is artificial intelligence? Let's go back to the question. How do you define artificial intelligence? Can you give a sentence of what, why, and how it is, this AI, in your opinion? So you don't need to Google, you need to be perfect, precise, just what comes to your mind. Yeah.
It's some machine output that approximates our thinking. You know,
Yeah. Yeah. Okay. Yes. Any other definition that you would like to share? Do you think it makes sense? Does not make sense? So yeah.
It's basically the same answer. Should pass the jury.
There is one approach that is more on the turning part. Yes. Machine learning can learn, an adaptive problem solving tool, not biologically. AI is the future. The future is now. Computational task learned from human input. Yeah, okay. Is the ability for a computer to learn and do certain things without us telling it. I find it very complicated without us telling it. You should always talk to them. Otherwise, they get too independent. Yeah. Others on the why, on the how. Okay, so let's, because it's okay. So okay, because it is the future. Yeah. So you can have fun feeling it, but let's go on the, let's say, on the kind of formal definition we can give. So the terms AI was let's say, appear for the first time in the 1956 in this workshop in Dartmouth, and it was invented by this American computer scientist John McCarthy, and used as a title of the conference. So as you can see, it's not a new term, right? So it's not, but not even too old. And we can define artificial intelligence as the subfield of computer science that models the mechanism of intelligent human behavior, how you say, right? We want to try this intelligent human behavior. But then I would ask you, how do you define an intelligent human behavior? What is intelligent human behavior? I don't know, because to be honest, I don't think that we have an intelligent human behavior, but no. You need to give also a definition of what is an intelligent human. So you need to give a definition of what is intelligence. And the definition of intelligence can change. And based on that, you can have different kind of subfield of AI. According to the European Commission's communication of AI, so this is, let's say, the European definition of AI that say that artificial intelligence refers to systems that display intelligent behavior by analyzing their environment and taking action with certain degree of autonomy to obtain specific goals. And as you can see, the AI can be divided in two parts. So one part we have more software oriented, and that one is more robotic oriented or more hardware oriented. So there is the interface between the software and the hardware. We have robotic, but also the big two blocks of AI are machine learning and reasoning. And the difference between these three blocks is that the reasoning part really rely on the idea that it's really think the mind as a Turing machine. So it really related to the computationalist kind of philosophical framework. And in this case, the intelligence is the intelligent human behavior, the mind, right, arise because we think that the knowledge that we accumulated can, and if we reason upon this knowledge that we accumulated over time, can help us in taking some decision for problem solving, and then this kind of related to optimization process or searching algorithm. And in this block, basically all the algorithms rely on the symbolic representation of the reality. And for example, we have, you cannot see there, no, it's too green. So we have, for example, the search algorithm, planning, scheduling, they only refer to the reasoning blocks. Then we have the machine learning part, and the machine learning part, it's more brain inspired in the sense that here the mind arises because there is a kind of interaction between these units in a network. And it's really more oriented to the neural network kind of way of thinking. And for the machine learning, the intelligence is in the data, in the sense that you are learning through the experience. So the data are a kind of representation of the experience that you can learn through that. So the reasoning and the machine learning have two different kind of paradigm of what intelligence is and what mind is. And you can use different kind of algorithm for both of these blocks. And then you say that yes, the machine learning is more related to the connection is kind of the connection is philosophical paradigm that actually say that the intelligence arises because of interaction of the unit, because of this network that we can build between computational units. And then we have the robotic part where the intelligence is embedded in the hardware, so it's more based on the idea that the information is physical, and then you have this kind of interaction between, for example, an agent and the environment, right? So-called reinforcement right of paradigm. So as you can see here, so AI, it's a very big field, and then the quantum computing can basically enter in each of those big blocks in different way, from the algorithm point of view, but also from the, let's say, application or application side. And the quantum AI, the quantum artificial intelligence is even more recent. It's very new, and people start to think about how can we then use quantum computer to perform AI. Basically, the idea comes because early in the 1996, Grover's proposed is a searching algorithm. I think everybody is aware of this algorithm, right? Who is not from the student? Okay, so, okay, there is someone that is not, okay. But basically it's an algorithm that allows you to perform the search in the space with better than the classical counterpart searching algorithm. But at that time, there were a lot of limitation in terms of the hardware. So yeah, there was not yet a clear idea of how and why to use quantum computer for AI. So only later on, for example, when IBM introduced the first cloud accessible quantum processor, then people start to think, okay, maybe we can we can build up some models that can perform machine learning on a quantum computer, but basically all the algorithms that were presented were kind of translation in quantum term of classical machine learning algorithm. And since COVID time until now, we could assist a very, let's say, a kind of a wave of money coming in, especially used by the big players like IBM and Google. And we can assist both to we can see the advancement happening from the technological side, but also from the theoretical side. And the focus nowadays in the field of quantum AI is really not only on the optimization, classification, generative models, but also in redefine what is learning for a quantum computer. Because what we saw before, we saw that how we define learning or intelligent behavior, it's not a unique way. There are different ways. Based on that, we can have different kind of algorithms and models. So we also need to think about how can we define intelligence that makes sense for a quantum computer. And this is quite a field that is always alive, let's say, also in the classical machine learning part. So the big question that we want to answer is, could the physical nature described by quantum physics also lead to algorithms that imitate human behavior? Who knows? Maybe yes. And what are the possibilities for the realization of artificial intelligence by means of quantum computation? Of course, these are the two big questions that we can narrow down and having, let's say, more affordable, more easy question that we can answer step by step in order to answer this big one. So what I'm doing in Maastricht is really try to use quantum computing for AI, but also try to use classical AI method for quantum computing, which is also a huge field. It's very important because it can be used for quantum computing itself, so for computational problems, but also for better understanding quantum mechanics. And in particular, so AI, as you can see, it's very built. So we have the reasoning part, the robotic part, but what I'm focusing in is the machine learning part. And why looking at quantum machine algorithm? Because first of all, you know that quantum computers are very good in performing linear algebra, but let's say that the hope is that quantum computer or quantum machine learning model can somehow generate patterns that are too complex to generate for classical computer, but also try to identify patterns that are classically intractable. And inside the blocks of machine learning, we can have different kinds of learning paradigm. The big three are those one, supervised, and reinforcement learning, but they are not exhaustive. They're not the only one. And actually, for example, the supervised learning will never work in a context which is supervised learning. All the real applications in machine learning are never supervised, because supervised means that you need to have all this data, and each data has a label attached to that. And then the goal here basically is to predict a label for a new data, for example, so you can use it for classification, for regression. And in general, the models that you use for performing supervised learning are called discriminative models. And example can be decision tree, random forest, super vector machine, neural network. And on the other side, the opposite side is that we have unsupervised learning. So I think everybody knows that you have data and you do not have labels attached to that. So this means that you do not anything about the structure of the data. So the first thing that you do in a supervised learning is try to identify some structure in the data. For example, you can perform clustering, and you perform a supervised learning using both discriminative and generative model. They are used for future extraction, dimensionality reduction, and examples can be Hopfield neural network or Boltzmann machine or Born model. So actually, what you end up working with is unsupervised learning setting or semi-supervised learning setting, which you only have these few data which are labeled. The rest are unlabeled. So at the end of the day, what you do practically when you use it in real problem is try to use a combination of these models to solve your problem. So most of the time, you need to understand the structure of the data. You need to do a bit of clustering before to do prediction. And then we have the reinforcement learning paradigm that it's really based on interaction between the agent and the environment. That means that the agent senses the environment, then based on this sensing, he performs some action. and he chooses this action from a set of rules that he has, and then the environment gives to the agent a kind of feedback, a reward function. And thanks to this reward function, the agent is able to learn by this interaction, then update its set of rule function, and then get better. But there are way much more learning paradigm. And why? Because we don't know what is learning. So we need, if we want to use this AI machine learning to implement what learning is, we need to first understand what is learning and how can we, what is an intelligent behavior? And these things are definitions which are quite blurry. You always need to tackle in a way that can be practical at some point, right? And so we can have quantum version of all of this kind of paradigm for the learning. And as you know, this picture explain the big 4 boxes that you can have in quantum machine learning, depending on which kind of data are you using, which kind of algorithm you're using, if they are classical or quantum. In my opinion, the most interesting block here is when you use quantum data with quantum algorithm, because I think it's the area in which you can have a kind of advantage in terms of understanding better quantum system, but also have some models that really use the quantum entities of your data. But the most explored boxes, let's say in the literature research, is the boxes that use classical data with quantum computer. And why? Yeah, because simply, we do machine learning using classical data, and then we just, the money that are getting in this field really would like you to use a quantum computer to make sense of the data that most people can afford, can have in their hands, which are classical data. So for this reason, this is the boxes that is most used. And inside this, let's say each one of those boxes, basically you can really apply, you can really think about quantum machine learning in different shadows. I put the 100 shadows gray of machine learning theory that you have there, because you can really use classical machine learning, right, to understand quantum system. You can think about how to enhance the training, how to enhance the inference, so how to enhance machine learning using a quantum computer. There is a lot of research also in the interaction between a system and environment, because the reinforcement learning really resembles the interaction, the quantum open system, where you have quantum system and then the environment, right? So there is a lot of work done in that regard. And then a lot also as well in the learning theory, more general. So what to address today? So the focus is real on quantum model. Yeah.
Ask a question. Sure. What do you mean by quantum data?
Quantum data, so data that are quantum entities, quantum state. So for example, if you think about the neutrino experiments in Japan, then maybe you can attach this neutrino to a quantum computer somehow. Or the LHCb, the Large Hadron Collider, they were thinking to attach a quantum computer to the new ring that they are going to build, but they will not do because they are not ready yet, they say. Or gravitational wave, maybe you have these interferometers, you can attach a quantum computer directly, but these kind of things nowadays are too expensive to do, and because still we do not have a clear idea if this quantum computer can actually really work in terms that can be useful for something, really. So, but yeah, I think that maybe at a smaller scale would be nice to have, I don't know, solid state physics experiments and attach this kind of thing to a quantum computer that directly can sense the quantum data that can have. I think this is the field that most, in my view, but maybe I can be wrong. I don't know. Yeah.
So quantum data is always more quantum physical process. Can you also quantize classical data?
Yeah, no, if you quantize classical data, then your input is a classical data, right? No, I think really that the data which is quantum in nature, so the idea is not translating your data in a quantum, right? You just want to take it quantum. I think it, for me, makes more sense, but I'm not doing anything in that regards. But if I will have time and the hope, then maybe if I will stay still in the quantum machine learning field, because I change a lot, then I will go to the quantum part. That's it, to the quantum box. Yeah. But today we're not going to talk about that. We're going to talk about classical data with quantum computer. And we are going to look at the quantum models mainly. Of course, when you have a quantum model, you have your data, then you have your model, then you can think about the architecture of this model, how calculated the gradients, how to integrate into the software, how to train the model, how achieve the expressibility of the model, how to study the generalization power of the model, and understanding the quantum advantage. So all these blocks that in general in the lecture back in Maastricht, I touch one by one, but here we do not have time, so we do a kind of blurry of bit of everything, okay? So what we are gonna look at today, I will give you a lot of definition, not a bit of definition, it's basically just a bunch of definition. We will study the basic structure of a QML model. We will look briefly at the data encoding technique and how this is related to kernel methods and beyond kernel methods. Little words in terms of training and expressibility. And then for your practical, I will just introduce this, the idea that I want you will work on Sunday. But we can do it together, okay? It's not that you have to do alone, okay? That's not... So I think I can skip the formalist part. You're all aware of those. And I will go maybe directly to the quantum models for AI. So there are two big blocks, near term and fault tolerant. Near term, that means that you have your model and you run it directly on the quantum computer that IBM will offer you. It exists in there. And the fault tolerant part is refers to all these algorithms that are there, but cannot really be run nowadays in the quantum computer because they need really perfect qubits and an amount of qubits that maybe is not affordable at the moment. And in each of these blocks, near-term and fault-tolerant, you can have both an hybrid or full quantum model. For example, in the near-term boxes, you can have hybrid model in the sense that one part is run on a classical computer, the other part is run on a quantum computer. For example, in general, the quantum models is run on the quantum computer, but the optimization of the model or the parameters of the model run on a classical computer. This is more general setup that you have. For the fault tolerant, instead, you have a classical machine learning pipeline, but you would like to substitute some subroutine with a quantum algorithm in order to accelerate the calculation. For example, you can use the Grover search or the HHL algorithm version of the matrix. And then you have the full quantum that, like as the words say, you directly run everything on a quantum computer, and you can have in both near-term and fault-tolerant approach. So the quantum machine learning system really, it's very simple kind of setup. You have your input data, you have a family of model. Actually, you never know which kind of model to use, right? In classical machine learning, you always try to use a bunch of those. The only, let's say, constraint that you have is the amount of data. In general, if you have a lot of data, then you go for the neural network. If you have few data, then you go for more robust machine learning, like random forest, which is most used one. And then for each of the model that you can choose, then you can do the parameters that you have, and then you can perform your task, classification, regression, and so. So you have your input data, your machine learning model that you need to tune, or find one that are the best parameters that give you the best, let's say, outcome. And then you have, let's say, the post-processing part. Now, the quantum machine learning part is exactly the same. The only thing that is changing here is that you have a slightly more, you have this part here, which is called encoding state preparation, that is basically the translation that you need to do from the classical data to quantum data. And then if you work in the classical data quantum algorithm setup, you need to have that. And that is the most important part of your algorithm in general. Then you have the processing that is happening with circuits, ansatz, parameterized circuits that manipulate your input state and then through unitary evolution. And then you have different kind of readout measurement part that can change depending what are you looking for. There are different techniques to read out your output. And in the NISC device, as I told you before, these kind of variational circuits that are also called variational quantum algorithm, parameterized quantum system, only refer to the same things, which is this part on the left here. In the quantum computer, you have each line refers to a qubits, and each of the qubits evolve step by step through this unitary. This unitary can be not parameterized or can be parameterized, and at one point you end up with a cost function that in which you that embedded the problem you would like to solve. This cost function depends on these parameters, so you need to optimize, minimize the cost function, and find the best parameter that give you the answer you're looking for. And then this loop continue until when you reach the minimum of the cost function. And the input and output can be whatever you want. So depending in which setting are you. So it can be some training data set, but can be also another cost function, can be an ansatz, another circuits. And the output, you can have a class for a new data. You can have the prediction for a new number, can be a probability distribution. And the three ingredients that you need to look at are the ansatz, so the architecture, the type of circuits that you're using, which it's really similar to the neural network that you see on the other side. So from the architectural point of view, these parameterized circuits are very similar to the neural network. But the neural network, basically they are activated by a nonlinear activation function, and then here in the quantum variational circuits, we only have a linear operation. Only the measurement part at the end perform the nonlinear activity. So don't be confused by these parallels with the neural network and quantum function, because actually, yeah, they are similar in the structure, just to make our mind easier, but they do not have anything in common. They don't have too much. So basically, the three things are the ansatz, the cost function. The cost function also need to be something that the cost function need to be something that a classical computer cannot reproduce easily. Otherwise, why you have to use a quantum computer? Should be quite complicated enough that makes sense to use a quantum computer to originate that one. And then the gradient. So also the choice of how you update your parameters also has an impact on the performance of your machine learning model. So the definition that we are going to give today are divided in two layers. Let's say the big one is deterministic and probabilistic, which is a little bit the same definition that you use for classical machine learning. So you have kind of models that are deterministic or discriminative or probabilistic. So in output, you have a probability distribution. And then after, we will give a definition that is slightly different, but let's say it's a layer down, let's say, about implicit, explicit, and data reuploading modeling that are reported in this paper down here. So deterministic and probabilistic circuits has the word say deterministic circuits. For example, the variational quantum classifier, you have an input to your data, you have your unitary that first encode the data, then manipulated the data with some parameters. Then what you obtain at the end is the expectation value, for example, of the label that you would like to associate in the case of variational quantum classifier to a new data. That depends on the input data and on the parameters of the model. And then in the probabilistic quantum model, instead, what you can have, so you still can have, you can also use it as a classifier, for example. You can associate a label given your input data, but in this case, you will have the probability of associating a label to that data, or you can use it to generate new data, a parameterized probability distribution given your input data. And a bit of definition here. So you have here your input domain and a parameter vector belongs to RK. Then your unitary. Your unitary can be divided into parts, as I told you before. You have the encoding part and the parameterized part. And each of these boxes can be complex enough in both the encoding and the parameterized part. So the two there. You have, sorry. So you have an alternation of parameterized and not parameterized gates, as you can see here, for both of them. And then this is the general way to represent both of those. So alpha can be X or can be theta. And then here you have these generators that basically you can express both of time evolution and Hamiltonian, where your Hamiltonian is this G that can be S or W. And of course, you need to have an observable, which is always an Hermitian operators. And then here is how let's say the formulation of your deterministic quantum model simply is the expectation value of your observable in the state that you create applying this unitary given by the encoding part and the parameterized part. And you can also express it using density matrix formulas in this way. And then I think nothing is new for you, right? For example, you can have a measurement at diagonal basis, and then if you plug in the M expression here, what you obtain that the models read like the sum of the possible value that your operator can have and the probability of having that value. And this kind of model needs to be run multiple times, for example, S time, in order to have a kind of precision in the estimated result that you will have. In order to sample all possible value of your observable can have. So of course the precision comes with a cost, because the number of times that you need to run the experiments can be sometimes quite high depending on the space that you would like to explore. So for example, if you have here as an observable the sigma z Pauli rotation, the sigma z Pauli rotation, how many eigenvalue can have? Do you know what I'm talking about? You are the only one that does not know. Or there are others from the students, I mean. You can express your, do you know what I'm talking about if I talk about the Pauli matrix? Okay, so you know that, okay. So the sigma z Pauli matrix, okay? So how many eigenvalue can have? 2, 1 and -1, right? So so how will the models looks like here? So you will have mu that can be 1 multiplied by the probability of measuring at 0 in the qubits that you have, -1, which is the other eigenvalue, multiplied by the probability of measuring a 1. So this is in the simple case where your observable is a sigma z Pauli. Your model is very easy, it's very easy. As an example here, so you have your input data, you have your encoding part that in this case is a generic rotation around the x-axis. And in this case, you can see that your input data, your number is encoded as an angle here. And in general, you always, the angle, you always need to divide it by 2, the angle that is in the rotation. So you obtain a new state here, and then you process this state vector with rotation of whatever you want. For example, in this case, you have 3 parameters, 4 parameters, you can multiple gates here. And then you obtain a new state here, and then you measure the sigma z Pauli that can be 1 and -1. So the models, if you do all the multiplication of the matrix and vector, reads like a sum of sine and cosine function, some of trigonometric function that we will see it later today. And you can define a threshold. For example, you can say, if you have here something that is positive, then you assign 1 label. If it is negative, then you assign the other labels, -1. So you can use it as a binary classifier, but also you can consider this, let's say your model, not as the one that assigned the label to your data, but for example, you can consider is as, for example, a density estimator. So you can use it to determine the probability of measuring at 0, probability of measuring at 1. So you can use it as a probabilistic classifier as well. Then you have the probabilistic quantum models that you can define in supervised and unsupervised setting. The difference basically is how you define your observable. So in this case, the eigenvalue of your observable refers to the possible outcome that you would like to have. So the output here is parameterized probability distribution conditional on your input. So based on your input, then which is the probability of assigning a label to a new data. And in the case of unsupervised instead, your measurement, your observable is the eigenvalue of your observable really related to your input data. And this is used basically as generative model, because in this case, you can produce a sample from your input data, but you can also play with that, because depending, for example, if you use basis encoding and some diagonal measurement, then you can have this unsupervised probabilistic quantum models expressed as a deterministic quantum models, okay? And they are used, for example, at the basis of Born machine. And as an example is the variational generator, which is inspired by Boltzmann machine, which is unsupervised settings. In this case, for example, what you would like to do, the goal is try to find, so let's see. So for example, you have this image 2 by 2, and you would like to represent this image 2 by 2, but instead of using 4 qubits, you use 7 qubits, but you only measure 4. So in this case, you have 4 qubits, which are the visible one, visible because you can measure it, and then 3 qubits, which are invisible, which are hidden because you don't measure it, okay? So you have this image 2 by 2 with 4, that is represented by in total 7 qubits, but you only look at 4. And then you start from the 0 state, then you make it evolve with a parameterized unitary gate, and you obtain this new state, and you measure in the sigma zeta Pauli. So what is the goal here? The goal here is to find these parameters theta that basically give you a model that is able to, you would like to find the state that depends on these parameters that maximize the probability of measuring here, for example, the bar or the strip. So you can see here that all the probability measuring only these 4 qubits of finding these bar strips are all very little, and only the one that are really the bar strip are high. So in this case, you find a probability distribution that really maximize the probability of finding this state here. So these 4 are really represented by this state. So these are the definition of discriminative and probabilistic quantum models, and you can also play between them in certain specific constraint. And we are going to look now at the encoding part, the state or state preparation part. Actually, it's not correct to talk about state preparation. State preparation is something that you have mainly when you talk about quantum algorithm. So when you talk about quantum machine learning, it's better to talk about data encoding, because it's really a translation that you do from classical to quantum data. State preparation is typical for quantum algorithm, because sometimes in the quantum algorithm, you don't need to start, you need to do this translation. You don't need to start from 0. Most of the time, you need to start from a specific initial quantum state that is not 0. So, so it's better to separate these 2 terms. And the data encoding, it's most of the time the bottleneck of the runtime of the algorithm, because in general, in quantum computing, an efficient algorithm runs in polynomial time in the number of qubits, and in machine learning, an efficient algorithm runs in polynomial times in the dimension of the data input. That can be, for example, n, each one with a number of future, for example, n by m. If you have a data set, you have, for example, n data, each one with m. Future that we like to extract. And most of the time you need to differentiate between amplitude efficient, qubit efficient kind of encoding algorithm. And the data encoding is very important because it's linked to the concept of feature map that we will see later, and this will link us to the kernel method that we will see later. But most of the time the data encoding as actually every time that you try to translate a classical data in a quantum state, you always need to do a lot of pre-processing tasks. So this pre-processing piece can add a lot of overhead when you look at your computational time. So when you try to use a quantum machine learning model, you also need to think, okay, are these data good for this? How much classical pre-processing I need to do in order to have this data represented in a quantum computer that will make me think, okay, if I use them after this model, these quantum models, I will have an advantage. So it's not always easy, okay? So let's start from n qubits, systems that are in the ground state. Then we have data that are accessible by a classical memory because you need to fetch it from there. You need most of the time some classical preprocessing and sometimes, for example, you also need to encode your label. So you have to think how many qubits you need to use in order to represent your input. And then if it's supervised learning setting, you also have to think how many qubits you need to use to encode your label and how you connect your input data with the label, right? In general, it's always a CNOT or entanglement that you do between them. There are different times. What time is it? 10 to 10. So how much time do I have?
Until 10:30, roughly. Yeah.
Okay. So so the basis, the data encoding technique. So these are the four basic one: basis encoding, amplitude encoding, angle encoding, and Hamilton encoding. But they are not the only one. So they are the basic. Okay. But if you, for example, you would like to represent an image. An image can be quite complex. It's one of the complex, also in the classical machine learning, when you would like to encode an image, actually most of the time you need to use a big computer because they can be quite big and complex. So there are different techniques that you can use for encoding an image, which are, for example, listed here. We are not going to go through this, but if you are interested, I have a study done that compare this technique on a specific image data set. Yeah.
So when you take the classification data, you cause some noise, and also when you choose those qubits,
yeah. Okay. So now we are talking about perfect. This lecture is very theoretical. So of course there is noise because the qubits are not perfect. The gates also does not evolve your state in a perfect way. So when you do a rotation of a certain angle, they never end up in the position that you are supposed to do, because when you put this model in a real computer, you always need to mitigate for the error, different kind of error. And there are different techniques that you can use in order to do that. Most of the time, it's very difficult to understand the source of the error, for where it comes. So all the techniques that are implemented in the software that you can use, for example, Qiskit or Penny, they have already some routine that you can use when you run your algorithm. And in general, they are kind of source agnostic. So you just use that, and then you end something. You will end something that is error mitigated, but actually you don't know from which source the error is coming in general, because they sum up. Of course, theoretically, you can distinguish it, and you can do an analysis, and you can think which kind of gates to use in order to mitigate that. But in practice, it's very difficult to discern. So you have this already implemented code that you can simply use together with your machine learning, or you can see it. Yeah, this is one of the problems. So it's problematic to represent data that are not corrupted, but we will see later on that this is a good question that will bring to the duty for the next lecture. So the basis encoding, okay, is the simple one. I will go a little bit fast. So it's very easy to prepare. You just need basically to flip your qubits. What you do, you have your data, you translate it in a bit string. The first one refers to the sign, then you have your fixed point, your real part, and after the common part. Then you can basically convert this binary string to a 0101 basis state. So you basically convert directly in a basis. And actually you need n gates, n qubits, each one for one of the digits that you have. It's very easy to prepare. what you have to do is, this is your bit string, you just have to flip your qubits at the power of this. So it's very easy, but it can be, especially when you would like to encode a database, it can become very sparse. So basically you use a lot of qubits, but actually you don't need to use all these qubits there. So it's not really, let's say, efficient in terms of number of qubits that you're gonna use. Then we have the amplitude encoding, that it's, let's say, very natural way of encoding. What you have to do, first thing, you need to normalize your data. Sometimes you also need to put 0 if required. You need less qubits. So for example, you need a number of qubits, which is a logarithm of n. N is your input feature. Okay, if you have a data set, then the number of qubits that you need is logarithm in that input feature and instance. You can encode both the vector and the data set, but the problem here is how to prepare an arbitrary quantum state. There are some algorithms, but the algorithms can be quite complex, and also depends which kind of algorithm to use, really depends after which kind of models you're going to use. So the angle encoding, so it's more suitable for representing continuous value. So use less qubits than the basis encoding, but can be expensive in terms of algorithms, because you need to use a lot of multi-controlled C0, and these one are quite expensive. Then the most used one in machine learning is the angle encoding. So basically, as the example that I showed you before in the variational classifier, you have this Rx, right? The encoding part, and the input data is encoded in the angle of your rotation. And you can play a lot with that. You can make it easier, you can make it complicated, but the important things to know about the angle encoding, that you cannot encode a data set directly. You need to encode one instance by one. And you can make it as complex as you wish, basically. You can also play with the values of the angle. You can multiply, you can do something fun there. And then we have the Hamiltonian encoding. So your input data are basically encoded in Ising type kind of Hamiltonian. It's one of the approach. It's easy to implement, but you can always encode specific type of data that fit this representation. Or if you have a data set, for example, this is your input data, which is saved in a matrix, then you can use this matrix to represent, let's say here, a kind of evolution of your Hamiltonian. But what you have to do before is die through, because not all the time your input data are Hermitian matrix, so you need to transform your data in Hermitian matrix, and you do it with this trick. So it's very similar to amplitude encoding, but of course, you really need something that can be encoded in this way. And some of the time also you need to think about which kind of qubit system do you have, which kind of hardware do you have. Okay, why data encoding is important? Because as I told you, especially when you are in the setting of using classical data and we want to analyze the classical data with a quantum computer, we need to translate this data. So what we do, we move from the space of real data, let's say, to the space of the quantum data. And what we do basically is a simple feature map. And the feature map sometimes can change the structure of the data in not a trivial manner, apart the amplitude encoding, because the amplitude encoding preserves the distance between the data when you map from your classical data to the Hilbert space. So every time we input our classical data in a quantum computer, we perform basically a future map. And then if we have a future map, then we can calculate the inner product if we are in a Hilbert space, and the inner product basically gives you a sense of how similar your quantum states are. So you can then build a distance measurement, and then if you have a distance, then you can perform learning. You can say these are similar, these are not similar. And the future map play a role in the kernel-based quantum models. So as I told you before, it's very important this happens just because of this translation that we need to do at the beginning. So the kernel methods in machine learning basically is based on the idea that this similarity measure or kernel can help you in basically represent a distance, and you can use this distance in order to perform learning. There are different ways of that you can build this kernel. When you move to a quantum computer, the kernel need to be difficult, not easy, preparable by a classical computer. Otherwise, there is no sense to use a quantum computer. A kernel is a function, right? Let's give a definition. It's a function, and this function defined this non-empty space x by x with value in the real space is a kernel if the Gram matrix enters are positive semi-definite. That means that given a subset of this space, input space, then there are some complex number that this equation is fulfilled. This is the kernel definition. Let's give now the future map definition. The future map definition is it's a future map that takes value in an empty space. The input domain takes value in a subspace of Rn, and it is nonlinear. So it means that this equality holds. Otherwise, if it's equal, if it's a linear map. So in terms of classical terms, so if we have a kernel, we have a future map, then there is a link between the kernel definition and the fact that if you have a future map in a Hilbert space, you can always define the kernel as the inner product of two future vectors in this Hilbert space. And this basically allows you basically to don't care anymore about the single entity here. So this the value that the future map gives to your input data, but what you care is simply directly the inner product of these two, which is the kernel. And this the kernel are widely used in a lot of machine learning model, especially the linear model. For example, here you have a linear classifier. The linear classifier, basically you have two bunch of data and you would like to classify a new unseen data, the pink one. What you can do, you can draw basically a plane that is divided these two data, but there are different ways of drawing this, right? Both of these draw will basically divide your data into parts that make sense, but they will classify in a different way your the pink dot. So how to choose the perfect plane that is divided your data in order to do the perfect classification? What you do, you maximize the margin. So you maximize the distance between the support vector. The support vector are the most difficult point that you have in your two data set. And so if you are able to individualize, so to spot which are the spot vectors, then you can basically define those and maximize the margin, the distance between these two hyperplane. And some of the time you're able to do this in your input data, like in this case, it's very easy, but sometimes your input data looks very complicated to be divided into parts. So what you do, you apply a feature map to your data. So you move from the input data space to another space, which adds higher dimension, that has an higher dimensionality. And then in this case, you are able to draw this line that divided into groups, your input data. And then you can apply, so omega t here refers to the equation of the plane of the line. And then you are able to assign correctly the label to unseen data. So mathematically, how do you do this? So you basically, you try to solve your primal problem. So you try to minimize this. This refers to the equation of the plane, and this part penalize all the points that are ending up in the wrong side of the two classes. You can look at the primal problem, but you can also look at the dual problem that you can obtain, basically calculate the partial derivative of the primal problem respect to the plane and to the B, which is called bias term. So what you end up is a maximization problem of the dual problem, in which, as you can see, you still have the Lagrangian multiplier here, but here you have this product between two future vector that is basically a kernel. So why it's convenient to pass from this primal problem to this dual problem mathematically in this case? Because in this case, what you need to know in order to assign a new label to an unseen data is the distance between this new data with the xi that are only the support vector. So you don't need anymore to calculate the distance of the points with all the data that you have into two classes, but only consider the support vector. So this kind of summatory here becomes much easier to calculate. You need to consider the kernel between the support vector and the new data. And of course, if this product here is efficiently computable, we can efficiently solve the dual form. So this is the so-called kernel trick, which is used for example, Camille, support vector machine. You don't need to know exactly how this future map works, but what you need to do is simply, if the future map gives rise to a kernel, so you can access directly to the kernel value, but not to the single feature map. Okay, this kind of linear model can be formalized mathematically. So if you have your input domain, the future map, then a linear model is defined as the inner product between the future map and any other elements of your future space. And as you can see here, now you cannot see, but this is exactly the definition of a deterministic quantum model, and in a specific space, which is the future space. So here to visualize a little bit what we saw before, so we define the kernel. The kernel is this function that can give rise to the inner product of two future vector. And then on the other side, we have the quantum models. The quantum models, so basically associate in the data encoding part, they associate to the input some quantum state, quantum vector in the Hilbert space. But this quantum vector in the Hilbert space can also be expressed in the future space if we consider the density matrix representation. So when we consider density matrix representation, then we can say that the quantum models are linear models in this data encoding future space, not in the Hilbert space. So basically, you can define the future map that assign the input data to a future vector, but also assign the input data to the density matrix. That for pure state, basically, you can express the density matrix as the outer product of the state vectors. So, okay, this is just a repetition of what I said there. So basically, so what we have here, we have a theorem that can be easily proved that if we have a data encoding future map over X, the inner product of two future vector is a kernel. So we are basically in the same kind of space of the map. So how we can summarize it is that a large class of supervised deterministic quantum models can be formulated as kernel method. The quantum models are linear models, not everywhere, but only in the future space of the data encoding future map. This is valid for both variational quantum models and fault tolerant model. Then what you can do, what is the advantage of expressing a linear model in this expressing deterministic quantum models as a linear model, is because you can use the kernel, and then basically you can apply all the kernel theory to these models. You can build also a kernel using a quantum computer, and this is called quantum kernel estimator. Okay, here just a summary that say, okay, indeed, this is basically the definition of deterministic quantum models we gave at the beginning, and basically what you show is that if you express it in terms of density matrix, it's also a linear model. So we can prove that the deterministic quantum models are linear models in the data encoding future space. And also you can express the measurement as a linear combination of the data encoding states. And there is a theorem that says that quantum measurement are a linear combination of the data encoding states. You can always find this optimal measurement that can be expressed in this way. There is another space that we can define, which is called reproducing kernel Hilbert space, which is basically made of all the function that maps the kernel all over the space. So once you fix one point, then this space is populated by the function that can be calculated the kernel between this point and all the rest of the point in your space. So mathematically, you can define basically this space as this function, and you can also define the inner product between function in this space. And I'm introducing this space because this space basically is equivalent to the state, to the space of the quantum models by definition, and which is linear in the future space. Okay, this is very definition based, but it's very easy. So seems complicated, but actually it's not easy. Just basically you can do the map of a linear model to a kernel. So the deterministic quantum models, a linear model through the kernel definition. And then remember that in the kernel theory, you have this reproducing kernel Hilbert space that is basically equivalent to the space of the quantum models. So to summarize, quantum machine learnings are linear modeled in data encoding future space, not in the space of the vector space, but in one of the density matrix. Quantum machine learning that minimize typical machine learning cost function have a measurement that can be written as a kernel expansion in the data. And the problem of finding the optimal measurement that a typical machine learning cost function trained with M data samples can be formulated as M-dimensional optimization problem. And we will see this in the training part. Before to go to the training part, basically just a few words, because I think, I don't know, what time is it? 10 past 10. Yeah, so I will be a bit quick. So as I told you before, in the variational quantum circle, three are the important things: the cost function, the ansatz, and how you calculate your gradient, how you optimize the parameters. So basically for each of those, we can so we can talk about for a long time. But before to talk about that, so first of all, you need to understand which kind of function the variational quantum circuits model can learn from a given ansatz. And how can you choose ansatz? There are different ways of choosing these circuits. It can be problem inspired, so you already know where your gate will be, where your qubits will be, and how your qubits will communicate to each other. Or can be problem agnostic. You just try different, let's say, ansatz that you would like to use. Or can be hardware efficient. So you would like to, you already know the connection between your physical qubits in your computer. So you are trying to create an ansatz that somehow makes sense for this particular structure of qubits that you have in your hardware, or can be variational Hamiltonian ansatz. So basically there are different ways you can choose your ansatz, and there is a wrong or correct one. Really depends on the problem and what you have there. And some of the time you would like to assess if your ansatz is good or not. So you look how expressive is your ansatz. And how you can do that, there are different ways. You can extrapolate a lot of index for your circuits. For example, you can compare the distribution of state obtained from the circuits, or you can count, you can measure how the entanglement capacity of your circuits, or you can extrapolate different kind of index. So there are multiple things that you can do in order to understand if your ansatz is good for your problem. In general, so you would like to have a trade-off between the expressivity of your ansatz and how it's able to generalize. And most of the time, so has been proved that more rotation you perform on your initial qubits, more complex is your circuits, more points on your space you will sample, you will explore. But this does not mean that it's good in terms of quantum machine learning perspective, because you can end up with overfitting. So what do you want? You would like to have a circuit which is expressive enough that allow you to explore enough points, but at the same time does not overfit. So it can be reused for solving a machine learning problem on a new data set. So which kind of function the variational quantum circuits give rise? So basically what they do, as we saw before in the variational quantum classifier, that the model function really reads like a sum of sine and cosine function. And this basically is simply a truncated Fourier series in which the coefficients here are related to the parametric part of your circuits, and the frequency are related to to the data encoding part. So basically, you would like to have an encoding part which is rich enough in order to give you a set of frequency that your model can explore, but at the same time, you also want a variational part which is not too shallow, not too deep, in order to give you a kind of good linear combination of the frequency that the model can explore. So when you design an ansatz, you also have to think about how you can calibrate your encoding part with your ansatz part in order to have a model that that has an expressibility which is good enough for the problem that you would like to solve. Okay, I will skip that. So, few words about how to train this model, because as I told you before, we can choose these ansatz, maybe understanding how deep, how many gates, how many parameters your encoding part and your parameterized part will have. Then we define the cost function, that is the one that encodes the problem we would like to solve, and then we would like to train the model. So try to find the parameters that minimize the cost function, the problem that you would like to solve. And how can you do this? How can you train the model to minimize this cost function? So first of all, the cost function should not be efficiently computed by a classical computer, otherwise why you have to use a quantum computer, should be operationally meaningful, and must be trainable. So how do you train it? So how do you train the cost function? How do you find the optimal parameter that give you how do you minimize the cost function that give you the optimal parameters? You can use automatic differentiation. So basically it's a chain rule, and your cost function depends on your model, right? And the model is a parameterized, depends on the parameters. So basically the chain rule gives you two parts in the partial derivative of the cost function. One part is the product of the quantum computation, the other one is the classical part. Now, what you want to do is try to calculate this partial derivative. So what you end up basically, so I will not go to, let's say the initial part, but you can read in the slides. So when you try to calculate the derivative, you end up basically with these two parts. But the problem here is that, first of all, you do not know that the partial derivative of this is a gate that depends on one parameters, okay? You don't know that partial derivative of this gate is indeed a unitary operation. And you do not know if these two parts here are valid expectation value, because you can see here that they are not symmetric. So what you do then, how do you calculate this? You use this parameter shift rule. So the parameter shift rule, basically, it's a family of rules that express the partial derivative of a quantum expectation with respect to a gate parameter as a linear combination of the same expectation, but with the parameter shifted. And basically, what you do, you calculate the quantum expectation value that depends on a classical parameters, and you sum it up. So basically, the partial derivative of the model that depends on some parameters is given by the weighted sum of the evaluation of the model at the parameter which is being displaced of a certain S. And this S can also be big. It's not small. So basically, what you end up when you calculate the gradient is an expression like this. And this is the estimation of analytical gradient, which is unbiased. Reminds a little bit of the finite difference rule, but the finite difference rule makes an estimation of the approximation of the gradient. In this case, what we have is an exact evaluation of the gradient. And what you do, basically, you evaluate your circuits with a displacement of the parameters. But the problem is that when you have a circuit that encode a specific cost function that you would like to use for machine learning, these circuits can be quite deep, quite long, and can be there a lot of parameters. So the update of these parameters never ends up to be done on a quantum computer using the parameter shift rule, because it's inconvenient. You cannot do this for all the parameters in the model if you have a lot of gates that have parameters. So you always end up in doing your optimization on a classical computer nowadays. But there is hope, let's say. Even though when you do training, if you're the training of your model on a classical computer, still you can end up in situation that you really you don't want to have. For example, the barren plateau, but also you have hardware noise. You also have this inherently stochasticity environment to the fact that you have to run your circuits multiple times. So there is some stochasticity related to the machine learning model. In particular, the barren plateau refers to the fact that at one point, you are in a landscape which is too big, and no matter what, no matter how you explore it, so you start from a zero state, then you manipulate it, and then you make it rotate a different angle, and then you go there to sample some points on this space, but you can end up in the situation that your cost function becomes any more independent from this angle, from this parameter that you would like to optimize, because the space is too big, and the rotation, even as helped you to explore different parts of the space, still it was not enough because the space is too big. So you ended really in a situation which is very flat, no matter what. So your optimization will not give you any kind of result. And it's also called kind of, so basically the variance of the derivative of your model function will basically vanish, go to zero, and all the gradients became concentrated to zero. So basically you will not do. But since before I told you that if you have a deterministic model and they can be think as a linear model, then they are basically kernel models, then what you can do that you can switch your training problem to a kernel setup. So you can use a kernel-based approach. And in kernel-based approach, basically, you can reformulize the trainings in terms of empirical risk minimization problem. So you can read it later, but basically the most important things here that basically you can find the optimal measurement in the future space that helps you in minimize the empirical risk of your model. The empirical risk is the difference between the outcome of your model and the real outcome that you are expecting. The problem is that you never know what is the real outcome that you expect, right? So for this reason, this is called empirical because it's based on the result that you got. And in this framework, there is the representer theorem that basically says that in the kernel setup, when you are in the reproducing kernel leader space, you can always find your optimal model, and this optimal model can be expressed as a linear combination of kernel that are calculated on your input data. So this means that in this reproducing kernel Hilbert space, even if you are in a huge space, in a very big space, you are always guaranteed that you will find your optimal model, your optimal measurement. So for this reason, considering the deterministic quantum model as a linear model and allows you to use a kernel-based training, because basically convert your problem, your optimization problem, in a convex problem. So you basically are always guaranteed, thanks to the representer theorem, to find your optimal parameters, your optimal solution, and it compare with the training of a variational quantum circuits, because in this case your cost function is very bounding, so you can end up in your optimization of the parameters in some local minima. Say that I will go very quick to this, right? There is another definition. So basically what we saw is that the deterministic quantum models can be expressed as linear models, and we can use all the theoretical formalism of kernel methods that can help us in say, yeah, don't think about variational quantum circuits, but for example, solve the problem related to the training, thinking about your model as a kernel method. But recently there's been this publication that say, okay, yeah, you can think about your model. So the one that we looked before, this variational kind of model, you have the encoding part, the parameterized part, you can think about this model, you can call it explicit, okay? Just a matter of name. You can call it explicit, in which you have your encoding part and the variational part. And you can express this model with the formalism that we saw before, right? So you can englobate, basically, you can express it as the trace of the density matrix and this, the measurement observable. And then we saw, okay, we can express this explicit model as a kernel model, which is called, in this case, implicit model. So a variational quantum circle is called explicit, a kernel model is called implicit model, in which you can get out here a model that can be expressed because of the representer theorem as a linear combination of kernel that can be expressed also in this way, if we consider the space of the density matrix, the future space. Now, what did they show in this publication? That actually, at the beginning, when I introduce you the deterministic quantum models, I introduce this as basically data reuploading model, because in the encoding part and the variational part, you have this alternation of encoding and variational part, encoding and variational part. And these models here basically can be expressed as the trace of a density matrix that depends on the data and on the parameters and your observable. It's similar to the explicit, but it's more complicated. So what they show here is that basically this data reuploading model is a generalization of the explicit model. So you can always reformulate this in this term. And then you can end up in, again, reduce an explicit model as implicit model, as a kernel method. And how they do that, basically, they do that with a cost. So doing this mapping from the data reuploading model to the explicit model. So basically, you would like to get rid of this alternation of data encoding and parameterized circuits, and you just would like to have two blocks, encoding first, parameterized circuits later. They can do this, they can translate this in this formalism, but it comes with a cost, and the cost is this new register of qubits that you need to use. So this means that you can do this mapping. It can be approximate in this case, exact in this case, but it comes with a cost. So you cannot preserve the dimension of your reader space. You need to increase it because you need new qubits, a new qubit register to use. I will not go into details of how they show that, but what is important here, that basically, so in this huge box of linear model, we have the model that live in this reproducing irreducible space that, and inside this space, we have both we have the implicit model, but also the explicit model can be there. And in particular, the data reuploading model can be also represented in this space. And they did this because they wanted to say that it's not true that all deterministic models are kernel models, as I told you before, because it depends a lot on the data encoding technique. Indeed, they show that in this case, here, what they use, for example, in this approach, they use basis encoding. And when you use basis encoding, you end up with a kernel that basically is represented by a delta Kronecker kernel. This delta Kronecker does not generalize very well. So basically what they to show is that it's not always good to translate, let's say, the explicit model or data reuploading model in implicit model in kernel method, because sometimes the data, this kind of explicit method can give you best performance in some specific case, depending on the data that you use and how do you encode the data. And they apply, so basically they did a comparison of implicit, explicit, and classical machine learning method. Implicit means kernel-based, explicit means variational circuits. And they compare the training and the test on a database, I think it's MINST database. What they show is that, yes, you can see that, for example, that let's say the implicit model can be better than classical, okay? But you can see that the explicit model here, which was a data reuploading model, can perform better than both. So from the theoretical perspective, there is this kind of reducing and simplify things, but still we are far in having a kind of theoretical framework in which we can really say this model is performing like this other model is performing better or worse, and still we don't really have clear why does it perform. So it's always good to be critical regarding what you find nowadays in the publication of quantum machine learning, because we are still building the theory around, and this it's, for example, something that show that. A few words to conclude. I think if you want to practice, and I think I suggest you to practice because it's the only way to understand how quantum machine learning works. I think Qiskit and Penny Lane, together with PyTorch and JAX, they can offer you a lot of, let's say, tutorial and guided, let's say, tutorial. So I think it's good that you put your hands on there. And to conclude, I think because we are there, right?
Yeah, we have like less than 5 minutes. So
okay. So to conclude, so of course, as you said before, so we are talking about, okay, the theoretical frame of this machine learning model, how can be interpreted, and which kind of tool from the mathematical words we can use in order to make sense theoretically of the model that we use. But we never talk about noise. But the noise, which is very important, is originated because of the interaction of the quantum system, particularly the quantum computer, with the environment. So for this reason, I would like to ask you to read this paper, which is a kind of review paper that talks about the benefits of open quantum system for machine learning. It's very, so basically it shows how can you use the open quantum formalism for performing classification, reinforcement learning, and reservoir computing. So you can read it to just understand a little bit. I think with all the open quantum system lecture that you have, you will be very easygoing with this paper. But what I want you to do for the next time is just focus on this paper, quantum classifier based on open quantum system with amplitude information loading. So we already saw what does it mean, amplitude encoding, right? And in this paper, they show you this approach that is able to perform classification, and the setting that they use, it's very similar to the to open quantum system, where you have some qubits that represented the closed quantum system and other qubits that represented the environment, and then you have a unitary evolution that in which you can encode your system data. So what I want you to do is that you form 4 groups, and how do you form 4 groups? It's up to you. Just let me know if you want that I form the groups. I can also do, but I think you can make your own groups alone. The only thing that I want is that the groups are more or less same number of people in. And I would like that you basically, we can discuss the paper together first. And then after we discuss the paper together, just to do an introduction, I would like that you challenge, improve, or modify what they propose there. And maybe one group is on the challenging part, one group is in the improvement part, one group it's modification part. You can decide what you want. But yeah, so we can discuss it together. It's up to you. You can write on the board, you can present a couple of slides, you can you can code, so you can do whatever you want. But it will be nice to see, because it's a nice exercise, because it puts a little bit together what you are going to learn during this school, which is about open quantum system, quantum thermodynamics. And if there is something that come in your mind that you can see, you can translate in a kind of nice idea that can be used in order to improve what is there, or challenge what is there, or modify what is there, then it will be nice to discuss it together. And if you have any questions in time, so if you want to have more material, or if you want that I give you more exercise, you just email me, okay? Or just talk to me later if I'm not in. So do you have any question or whatever? Just email me or ask now if you want. Yeah.
I just want to know if the slides will be uploaded to
Yeah, they will. I don't know how, but yeah, I think they will, right?
If you email me your slides, I can put it on the
Yeah.
website.
Okay, good. Yeah.
Okay, let's thank the speaker.
Thank you.
Do we have any questions?
To find out, in one of your slides, it mentioned that in the graph of the cost function, might have the local minimum. So how do you because here the cost function is not the minimum, it's one. Yet it's the forced minimum. You might find yourself.
So this is the landscape of the cost. So basically, when I show you this graph, so basically it's the value of the cost function with the difference value of the parameters, right? Let's say it's the theoretical one. It can have some minimum. Yeah, it can have because it's the value of the cost at different set of parameters you can have in your model. Yeah, but
how do you know the cost function? It's because you try to minimize the cost function.
how do you know that the shape is like that? So how do you know that is like as more minima?
The cost function, like if you want to find where the cost function is minimum, yet the local minimum sometimes may above not. So it's not the definite, the true minimum.
How do you distinguish between local and global minima?
Ah, okay, yeah. So how can I distinguish? So how can I find them? So what is the the global minima is the real minimum that you would like to end up, right? What do you mean how to distinguish? So you would like to, so the optimization is there to find the parameter set that bring you to hopefully to the global minimum of your problem. But you don't know if you are going to reach that, right? Because the parameter space can be quite wide. You do not have access to the real cost function. You have the empirical, let's say, your empirical landscape that you would like to explore. Right? We don't know how the true one, and how to distinguish between the global and minima. It's basically, so yeah, you explore it. You explore the value of the cost function, different parameters. For this reason, you have this this optimization, the optimization part, and then it's the one that, so the global minima should be the one that is giving you the smaller value of the cost function. Yeah. And the problem is exactly that you can be trapped in one of the local minima, which is not the global. So for this reason, for example, one of the solutions that has been proposed is try to translate your problem in a convex optimization problem where you are guaranteed that there is only one minima, and then it's easier to reach that minima that, I mean, yeah. I don't know if I answered the question or not. Okay.
So
Yeah.
Oh, sorry. Yeah, it's a related question, but maybe you just answered it with your final comment there, because I guess for some optimization problems, you probably can define algorithms that will provably take you to global minima, but that's only for very certain types of problems. So is that possible in this situation?
To find
To define, are there any situations where you can provably reach the global minima? So some optimization problems you can do that, but it's only very specific classes.
Yeah, so kernel minimum guarantee you to find the global minima, but yeah, sometimes you don't want to. So for the machine learning part, so it's very rare that you will find the global minimum of your problem. So actually you never find that because, I mean, also from the classical point of view, you don't need to be quantum machine learning more, but also classical machine learning. Sometimes you don't want to find the global minimum, but it's very difficult to do, but something that is at least close to that will be good enough. So yeah, okay, these formalities that translate this particular model in kernel that guarantee you that you will find the global minima for sure. Yeah, but
so you don't
this does not mean, yeah.
You don't actually need to, you just need to find what is good enough, essentially.
Yeah, machine learning is very heuristic. So it's, but yeah, there is this kind of, no, if you go on the kernel method, yeah, you are basically guaranteed to find that one. For the variational part or other kind of machine learning type, no, you're not guaranteed. Maybe you will find your optimal somewhere close by, but it's not the global minima, but it's good enough depending on the application that you will use it for. So it's not important to be perfect. Yes. Yeah.
If we have any further questions, you can maybe ask Menica during the break. So yeah, let's thank her again.
Thank you.
So yeah, did Francesca? Yeah. Okay. We reconvene at about 11.
there's a fair amount to get through today. We'll see how far we get. So originally this was the course of 4 lectures. The 4 lectures were only 45 minutes each when I gave them previously, so I thought I'd easily get through them this time, but somehow I've managed to stretch the first 2 lectures to an hour and a half. So sorry, no, to 3 hours. So we'll see how far we get with this today. I'm hoping that we get onto the density matrix and decoherence, because I'd like to discuss a bit about how the open systems formalism comes into play with quantum interpretations as well, to link to some of the other aspects we've heard about in some of the other lectures so far. But what we're going to start with is this third topic, which is primarily around the measurement problem, contextuality of measurements. And then I'll say something very brief about objective collapse models, because they are kind of open systems models as well, at least phenomenologically so. And then, as I said, let's see if we can get through the density matrix and decoherence. I'll probably skip consistent histories and maybe say something on many worlds, but I don't have anything detailed on that. Okay, just as a brief reminder, in the last lecture we talked primarily about Einstein, Podolsky, Rosen, so the notion of reality, locality, and completeness, and the fact that they conclude from an argument based on entangled spin pairs that quantum mechanics is not complete. And we saw that this can be tested via Bell inequality experiments, and the violation of Bell's inequality in quantum mechanics tells us, or one way of interpreting that is that quantum mechanics is incompatible with local hidden variable theories. And we also discussed one possible hidden variable theory, which is the Bohmian mechanics, which is a non-local hidden variable theory. So it's compatible with Bell's inequality by its non-local nature. We're going to start this lecture with a related concept, which is that of contextuality. And actually, there's a very strong link, or in fact, they're kind of intertwined between Bell's inequalities and contextuality. You can see Bell's inequalities through the lens of contextuality as a kind of extension of contextuality to entangled spin pairs, for example. So the question, which is very similar to the question we were asking in our derivation of Bell's inequalities, is whether measurement values are predetermined in quantum mechanics, and are they independent of any other measurements being made simultaneously. So if we consider 3 operators, A, B, and C, with which we're defining some observables, we're making some measurements, and we make a measurement of A. So let's consider all of A, B, and C commutes, so we can measure them simultaneously. If we make a measurement of A with B simultaneously, and we make a measurement of A with C simultaneously, do we get the same measurement outcomes? So does it depend on independent measurements that we're making at the same time, what we get for A, or are the values predetermined so it doesn't depend on what else we're doing? And that's kind of the notion of contextuality. And the context in contextuality comes from specifying the setup, the measurement context in which we're performing these particular measurements. So if the measurement values are predetermined and they're independent of any other measurements being made, then we call the theory non-contextual. And if the measurement values are not predetermined and they're dependent on other measurements being made simultaneously, then we call them contextual. And we're going to show that quantum mechanics is contextual, and we're going to outline a proof that's a bit like a Lucian-Hardy-like proof of non-locality. So I mentioned very briefly that Lucian-Hardy has a non-locality proof that gets rid of some of the counterfactual reasoning within Bell's inequalities discussions. So we can also apply these kind of methods to a quantum contextuality proof as well. So we're going to consider a simple setup and use our kind of classical logic to infer some properties of a system and then see where the quantum mechanics adheres to that logic. So let's consider a single physical system now. We're not talking about entangled pairs, just single physical system. It could be quantum or classical at this point. And we can make 5 true or false statements about it, and we'll call those statements A1 to A5. And the system is going to be prepared in such a way that the following statements hold. So the probability of getting A1 as true, so each statement is true or false, remember. The probability of getting A1 as true and A2 as true, if we measure both simultaneously, is 0. And that's given by the first condition. Likewise, if we measure A2 and A3 simultaneously, the probability of getting both of them false is 0. The probability of getting A3 true and A4 true is 0. And the probability of getting A4 false and A5 false is equal to 0. So if the true or false results are predetermined and independent of which questions are being asked, i.e. if the theory that we're interested in is non-contextual, then the following reasoning holds. So let's go through that reasoning. So remember these statements. So number 1, so if A1 is true, then A2 must be false because the probability of A1 and A2 both being true is 0. If A2 is false, then A3 must be true because the probability of A2 and A3 being false given by the second condition is 0. Okay, then if A3 is true, by our previous logic, then A4 must be false because the probability of A3 and A4 both being true is 0 by condition 3. And then if A4 is false, by our previous logic, then A5 must be true because the probability of A4 and A5 both being false is 0. So we deduce then, starting from A1 and going through the steps of the logic, that if A1 is true from the beginning, then A5 must also be true via each of these steps according to these probabilities. And so the probability of A1 being true and A5 simultaneously being false is 0. So does quantum mechanics adhere to those probabilities? That's what we're going to look at. So the answer obviously is not, because otherwise I wouldn't be telling you about this. But let's look in a little bit more detail about how we can explore this in a quantum mechanical setup. So we're going to consider a quantum system in some arbitrary state psi. And we're going to identify the state A1 as a state of that system with property A1 being true. So that means it has measurement outcome 1. And measurement outcome 1 corresponds to measuring that property as being true. How do we get a probability then of something being true? Well, it's the modulus of the overlap of the state of A1 with our given quantum system state squared. We can write that. So the modulus squared. So we've got modulus overlap of A1 psi squared as the probability. That's equal to A1 psi A1. Okay. We can call this. No, I want to write it the other way around, don't I? Sorry. Psi A1 psi. Okay, that's equal to this. And so we can call this a projection onto A1. So we call this P1. So we can write the probability that A1 is true as the expectation value of this projection operator onto the state A1 that defines our property A1. Since A1 is either true or false, the probability of A1 being false must just be 1 minus the probability of it being true. And that can be written as an expectation value if we take P1 and subtract it from the identity, then that will give 1 minus the probability of it being true. So it'll give the probability of it being false. So this is our kind of mathematical setup for testing this within quantum mechanics. Yep.
Are going to be difficult. Actually, my neighbor here that cultivated.
Just make sure she has a.
Okay.
Thank you. No, because she was clever about that. You're taking an incident and you're showing the contextuality from a particular case.
Yeah.
So in essence, that doesn't have to hold for all cases. So you could say that, okay, in this particular case that you're going to prove, there's contextuality, but how do you prove that it holds for all cases?
It doesn't, I mean, I don't need to prove that it holds for all cases. If it holds for even a single case, it means that quantum mechanics is contextual. It doesn't mean that every situation that I ever consider is contextual. But
because that's a definition.
Yeah, because the theory is either contextual or non-contextual. And the only way to prove a way to prove that is contextual is just to come up with a single example that it is. Of course, it's not the only example, but but there would be situations where I could define states where the previous logic would be true as well, and that's fine. It just means that one has to be careful about making non-contextual statements without being clear that the situation you're considering can be considered to be non-contextual.
Right.
Okay, so we have a way of mathematically representing these different outcomes and the probabilities associated with them. We can apply exactly the same reasoning to properties A2, A3, A4, and A5. And then obviously to ask simultaneous questions, because we had the probabilities of simultaneously measuring A1 to be true and A2 to be true, we just tensor product together these projectors for the different questions being asked. So that definition here would be the joint probability of A1 being true and A2 simultaneously being true. Importantly, we need to construct these projectors such that 1 and 2 commute, 2 and 3 commute, 3 and 4 commute, 4 and 5 commute, and 1 and 5 commute. And that's because if we want to ask simultaneous questions in quantum mechanics, the questions we're asking, the operators that represent those measurements, have to commute in order for us to be able to ask them simultaneously and ascertain given values, true or false values. The reason that we define these commutators as 0 is because these are obviously the only ones that we're defining as having joint probabilities here, 1 to 4, and then our final joint probability, which is number 5, which we're trying to test, is whether probability of A1 being true and A5 being false simultaneously is 0. What that means is that these are the only commutators that need to be 0. So commutator between 3 and 5, for example, can be non-zero. It doesn't matter. We never ask those questions simultaneously. Okay, I'm going to upload a more detailed example of this. So you don't need to kind of worry about all the detailed maths at this point, but this is just to show an example that was given by Cabello and co-workers in 2013 of a simple system that shows contextuality. So it's a 3-level quantum system, and they take this particular initial state, and then they define different projectors, A1, A2, A3, A4, and A5, all of which have eigenvalues 1 or 0, if I remember correctly. So where 1 represents true and 0 represents false. So with this setup, one can go through the calculations and construct all the relevant projectors and check the necessary commutation relations are fulfilled, and they are. And you can also verify by constructing those projectors and taking the expectation values in the state that we define that each of these probabilities is fulfilled 1 to 4. However, if we calculate from these states the probability that A1 is true and A5 is false, we get the answer 1/9, which is not equal to 0. And so that shows us that quantum mechanics is contextual. We can construct situations where the logic that we applied from the probabilities previously doesn't apply in the quantum mechanical case. And so the probability of measuring A1 and A5 simultaneously doesn't logically follow from the probabilities of measuring A1 and A2 simultaneously, and so on, which means the behavior of A1, for example, is dependent upon whether we're simultaneously measuring it with A2 or we're simultaneously measuring it with A5. So the theory is contextual. Like you say, and it's a good point to reiterate, it doesn't mean that every single situation that we construct will behave in a contextual manner, and certainly one can construct. I mean, you saw on the we go back. You know, this is not an intuitive set of states one would necessarily write down as some particular example. And I don't know how Cabello and co-workers necessarily came up with it. What's nice about this is it's a relatively simple system because it's just a 3-level system. But no, it's not a 2-level system example. So they had to go to a 3-level system case to show it in a simple system here. So quantum mechanics is contextual because there are situations in which the non-contextual reasoning doesn't hold. And actually, you can see Bell's inequalities through a similar lens as well, in terms of making measurements on one part of an entangled pair simultaneously with another part of the entangled pair, and how the behavior depends on which measurements are being made simultaneously. So the example proves that quantum mechanics is contextual, and so it's impossible to assign predetermined values independent of the questions being asked to all physical properties of a quantum system. So what does that mean? Well, it means for hidden variable theories that, as well as local hidden variable theories being impossible, at least in terms of the usual interpretation of what Bell's inequalities are telling us, contextuality implies the impossibility of descriptions in terms of non-contextual hidden variables. So it looks like any hidden variable description that's going to reproduce quantum mechanics has to be both non-local and non-contextual. So probably as confusing as quantum mechanics is in the first place anyway. If you want to see more formal discussions of these kind of contextuality proofs and well, further aspects of it, then I encourage you to look up the Cohen-Specker theorem. Okay, so now we've determined that, we've determined that measurement outcomes are not predetermined, that the active measurement somehow brings those outcomes into being. So let's discuss a bit about the active measurement itself, and that highlights what's termed the measurement problem. So we're going to look through a bit about what the measurement problem is, von Neumann's ideal measurement scheme, which highlights issues in interpretation or in the dynamics of both quantum systems and measurement when one applies quantum mechanical ideas to measurement. We have to talk about Schrodinger's cat because no discussion of measurement would be complete without some discussion of Schrodinger's cat. And then I may go into a little bit of an introduction to objective collapse theories. Okay, so we've seen from our discussion in the first lecture on the postulates of quantum mechanics that measurement seems to play a special role in contrast to classical physics, although Bohr may have argued against that. But let's take the point of view that measurement plays a somewhat special role, at least in the way that we define it mathematically. So we have to first define what a measurement is. And one definition we could give is an irreversible operation on a system which determines the status of one or more physical quantities as recordable data. So let's take that as our definition of a measurement for now. So there are various aspects to the measurement problem, and they can sort of be defined by these three different bullet points here. So we already know that measurement induces non-unitary evolution of the system. So the question is why that's the case. In particular, if the measurement apparatus is made up of atoms, they should be expected also to obey the standard quantum mechanical evolution laws. So why should the system plus apparatus not just evolve unitarily globally? On the other hand, we see definite measurement outcomes. You know, we go to a lab and we see a signal on a oscilloscope or whatever. I mean, this is showing my naivety about experimental physics, I'm afraid. But whatever it is that one is looking at in the lab, some photons hitting some photodetectors or something like that, we end up seeing some definite measurement outcomes. You know, the photon was present at some point and triggered a cascade of electrons. So the projection postulate and wave function collapse somehow appears necessarily within the formalism. So we could start by asking whether collapse of the wave function could just be the result of solving the Schrödinger equation for a very large number of particles, so for macroscopic systems, and then effectively unitary evolution would be giving rise to collapse, and so we wouldn't have to give it as an extra postulate. But unfortunately, that's not the case. The time-dependent Schrödinger equation is linear, but the amplitude of the post-measurement state depends non-linearly on the initial state, because when we apply one of these projection operators, such as this operator, to a state, it becomes unnormalized, and we have to renormalize it by dividing by that square root of the expectation of the projection. And there's no way to get that state from a linear equation like the Schrödinger equation. So we can't just postulate that that Hamiltonian evolution gives rise to projection when applied to a large macroscopic system. We need another form of evolution. Actually, von Neumann decided to take the opposite view of Bohr and Heisenberg and so on, and instead of considering measurement apparatus as classical, he was interested in what happens if we naively just apply quantum formalism to both the system under investigation and the measurement apparatus themselves. Not because he necessarily thought this was the right way to describe measurement, but because he thought it was a good way to highlight some of the problems of measurement within the quantum formalism. So it's now termed the von Neumann scheme for ideal measurements. And yeah, it highlights some of these issues a bit more concretely or mathematically. So the setup is that one has a system, and the system is in some state SI for initial state, S subscript I, and then the apparatus is also considered a quantum system, and that's in some state AR, which is like the ready state of the apparatus, and we also consider that to be a quantum state. And then the interaction between the system and the apparatus takes the apparatus from the ready state, so the ready state you can think of as a state where nothing has been measured, that the apparatus has been reset, and then it's in a position now to measure something. And then given the system state SI, a good apparatus will then move to some other state, AI, that records something about the properties of SI. So that's why AI has the subscript I. So it's a state of the apparatus that tells you the system was in the state SI. So here's a simple example. So let's take a superposition, some system state that is a superposition of spin up and spin down in the Z basis, with a apparatus in the ready state. We know that the linearity of the Schrödinger equation will ensure that over some time frame, the evolution will take us then to an entangled state of the system and apparatus, because the apparatus will record a state A up for the system in the up state and a state A down for the system in the down state, provided the apparatus is able to distinguish between the two. And of course, we make that assumption, otherwise it wouldn't be a good representation of a measurement device in the first place. So what we see then is that the superposition that was present originally in the system only has been amplified after the interaction between the system and the measurement apparatus to the level of the macroscopic apparatus as well. It's not clear at this point how to regard this dynamical evolution as representing a measurement. So it's not clearly given us one single outcome, for example. We just have this entangled state of system and apparatus. There's another aspect of this that causes difficulties. There's an ambiguity in writing this state, because the superposition of, the entangled state of the spin and the apparatus in the Z basis can equally well be written as an entangled state of the system in the spin in the X basis. So it seems as though the apparatus has then formed one-to-one correlations with both the Z and the X spin components of the system. And in fact, you can write it for any arbitrary spin half basis. So you could take any linear combinations you want, and you will get one-to-one correlations between the spin in that direction and the apparatus states. So a preferred basis for the measurement is not explained by the von Neumann scheme. And so we need to appeal to other mechanisms. And one of those might be decoherence inherent to the measurement apparatus, for example. And we'll talk about that in a little bit. Okay, I said we have to talk about Schrödinger's cat. So I guess everyone's familiar with Schrödinger's cat thought experiment. Actually, Schrödinger's cat was so Schrödinger put across this thought experiment originally, I think, slightly from a misunderstanding of von Neumann's viewpoint with the ideal measurement scheme. So Schrödinger's aim was to show that if you apply quantum mechanics to both the evolution of a system and a measurement apparatus, you get absurd conclusions. And I think this was sort of in response to von Neumann's ideal measurement scheme, but I think he didn't really understand that von Neumann was not saying necessarily that one should apply his measurement scheme to understand measurement, but rather that it was a way to clarify the issues of measurement in quantum mechanics. But anyway, it does highlight some of the issues with the ideal measurement description. So we imagine a cat in a box, and the decay of an unstable atom triggers a hammer to break a vial of poison that then kills the cat. Poor cat. According to quantum mechanics, the state inside the box should be a superposition of the atom not decayed, the cat alive, or the atom decayed and the cat not alive, in contrast to everyday experience. So if we apply that ideal measurement scheme that I just discussed, we would get a superposition of the microscopic atom, either decayed or not, and the macroscopic cat either alive or dead. So if an observer opens the box, then they perceive only one of those states. So there seems to be some kind of collapse of the wave function. But it's hard to say what the state of the cat was before the box was open. Was it alive or dead or both or neither somehow? I mean, there's not a clear notion of that. You know, you can also add other questions like whether the cat can make an observation themselves of whether it's alive or dead. Does it need to know about quantum mechanics in order to know whether it's alive or dead or not in that situation? So essentially these questions were highlighted in order to show the absurdity of trying to apply these kind of notions, or in Schrodinger's viewpoint, applying these kind of notions to the measurement of quantum mechanical properties themselves. Okay, so that sort of highlights that there are multiple aspects to the measurement problem. There's not only collapse of the wave function, there's what sets a particular basis in a measurement and then gives us out, for example, measurement outcomes along Z or along X or along any other spin basis if we're doing spin measurements. And there's also the question of why we get particular values. So we see single values, we don't see superpositions, for example, or well, we get a single value out when we make a projective measurement of a particular quantity. Okay, so I'll say a little bit moving on from measurement about objective collapse theories. How are we doing for time? Oh, we're doing okay. So objective collapse theories actually really are theories in their own right. So they attempt to solve the measurement problem by postulating a different kind of dynamics to the unitary Schrodinger equation dynamics. And the reason that they're theories in their own right is that they make predictions that are at odds with standard quantum mechanics. And we can say a little bit more about that later on. But what that means is that they are actually testable, or in principle testable. So they embrace the projection in an ontic approach. So they consider, remember, ontic was considering the quantum state to correspond to something that's underlying reality. So it's a real property of a quantum system. It's not a statement of our knowledge of the system. And without any hidden variables. So there's no hidden variables within the theoretical description. What they do is they add a physical mechanism to explain collapse, and usually that mechanism is just added phenomenologically. And to give a kind of link to some of the open systems theory we've heard about in other lectures over the course of the week, often that collapse process will be included by some kind of Lindblad operators within a master equation formalism. For example, trying to project the system onto position basis or some other basis states. For the most well-known collapse theory is the GRW theory formulated in 1986. And that has a formalism whereby, in addition to the unitary quantum evolution, particles occasionally collapse their state spontaneously. So it's like a kind of spontaneous emission process, except it's not emission into some electromagnetic field. It's a spontaneous collapse in some basis. And actually in the GRW theory, it's in the position basis. So they prefer collapse into specific positions. So the way that the theory is set up, the rate of collapse is such that for individual particles, the behavior is never observed in practice. It would take more than the age of the universe for that collapse to happen. But for large objects, the rate the rate rapidly increases, and spontaneous collapse then causes the quantum state of the entire object to behave classically. So if we couple a small object to a large object, then within the theory, the small object inherits the rate from the large macroscopic object, which then collapses the wave function of the microscopic object due to its interaction with the measurement apparatus. And so that's how measurement occurs within the theory. As I said, it's a theory. It makes testable predictions. In particular, it limits the size of superpositions. So one could test how large a superposition one could make to try and rule out particular collapse theories, for example, or particular regimes of parameters for collapse theories. Yes, so I kind of mentioned this earlier. So Schrodinger's equation is modified within GRW theory. So the fundamental equation of quantum mechanics is no longer taken to be the time-dependent Schrodinger equation, but it's taken to be something that includes nonlinear stochastic terms, which looks essentially like a master equation written in the position basis. Obviously, this is not a unique choice. The GRW theory is phenomenological. It doesn't postulate any microscopic mechanism that gives rise to this collapse. It just says the quantum mechanical laws are such that one should start the foundation of quantum mechanics with this kind of evolution equation rather than postulate a Hamiltonian unitary time evolution. Obviously, that's not unique. One could postulate collapse in any basis one wants, and there doesn't seem to be any principle necessarily to choose between the two, apart from experiment. So there's a strength that sets the timescale for collapse. And as I said, the rate scales with system size, so the number of constituent particles. So for larger systems, you get faster collapse. And there's also another parameter within the model which sets a length scale below which collapse doesn't occur. And that's meant to sort of separate microscopic and macroscopic length scales. So because the theory is phenomenological, we don't really know how to set these parameters. All we can do is say, well, if we suggest various parameters, we get predictions from the theory that match our kind of current understanding of quantum mechanics. But it doesn't really rule, well, it doesn't really provide any strict basis for choosing these parameters apart from ruling out particular regimes of parameter space because they're incompatible with our current measurements on quantum systems. So in the original paper, GRW suggests a length scale of around 10 to the minus 7 meters to separate microscopic and macroscopic. So collapse is effective for larger length scales than that. And they suggest a rate of about 10 to the minus 16 seconds, inverse seconds, which gives a time of about 3 times 10 to the 8 years for microscopic objects. And then macroscopic objects, the rate scales with the number of objects, the number of particles squared, actually. And then the rate is increased such that for classical, for things that we see as classical, as macroscopic, then collapse is effective on very short time scales. Other suggestions for parameters in the literature vary by orders of magnitude, so there's no agreement really on what these parameters should be. And in the end, the validity or not will need to be determined by experiments. Okay, so in this section, I've introduced the measurement problem in quantum mechanics and highlighted several aspects of it through von Neumann's ideal measurement scheme. We discussed briefly Schrodinger's cat that aims to highlight the absurdity of applying quantum mechanical thinking to both the dynamics of microscopic systems themselves and the measurement apparatus that are macroscopic. And then we discussed collapse models, which introduce a phenomenological collapse mechanism, but without really some kind of microscopic formalism behind it. Although I should say that there have been some suggestions that perhaps gravity could play a role. So I think particularly Penrose has been interested in this over a few years. And one reason is that it's nonlinear and its strength scales with mass. So it might give a situation where we do see a scaling of a collapse rate with the size of a system, you know, between microscopic and macroscopic. Is that a question? Well, we're going to come on to something like that now, where we're going to talk about decoherence, actually. So we're going to talk about interactions between particles and their environments. For a macroscopic system itself, unless it has some environment with which it interacts, we can consider it, you know, if it's prepared in some kind of pure state, we can consider it as evolving into another pure state. And so then we don't get a kind of measurement out, you know, we get the von Neumann scheme essentially. Of course, you can argue about whether one could ever prepare a macroscopic apparatus in a pure state, but again, the reason you wouldn't be able to is because of interactions with what surrounds it. If you had something that was somehow isolated, then you would assume that it would be in a pure state. But we know we can never isolate it because even in a vacuum, we have electromagnetic fluctuations, for example. Okay, so I'm not doing too badly for time, I think. So I will at least hopefully be able to go through the next part on the density matrix and decoherence. And thanks for the question, because it brings me on nicely to that. I'm probably not going to go through consistent histories in many worlds, but that's okay. I've probably gone through enough stuff already anyway. Are there any other questions at this point before we start talking about the density matrix and decoherence?
Oh, sorry. That should be more. Yeah. So yeah, with the formalism where you include this like nonlinear stochastic term, I'm assuming there's like some kind of major consequences of having a nonlinearity in quantum mechanics. Like, is there any?
Yeah. So the one big difficulty is you lose conservation of energy. So people have tried to get around that in some ways. One, by saying that it's sort of conserved on, like maybe conservation of energy actually doesn't hold, and that it's just, you know, on timescales that we believe it holds, but actually fundamentally it doesn't. That's not that satisfactory, but I guess because our notions of conservation laws are based on symmetries of Schrödinger-like evolution, one could say, well, if I do fundamentally change that evolution, then those symmetries don't exist anymore. So I've got no reason to believe the conservation laws should exist anymore. Yeah, so that's one particular problem that's difficult.
Yeah, I'm not sure if it's related, but you could kind of postulate that fundamentally everything is open, and so therefore you mentioned that the problem is that you don't have this energy conservation and things like that, and you could like potentially postulate this stochastic term originates from the fact that fundamentally you can treat things as, you know, you can't isolate anything fundamentally, and
yeah,
that it's intrinsically open, and so therefore but yeah, because the reason I mention that is because Francesco always tells me that he has this idea that everything is open, and that the problem that I've had with that is that then how do you deal with things like energy conservation?
Yeah.
Like,
so well, now we're going to talk about open systems in the more traditional sense of interactions between some small system and some large environment. But there's a distinction between the kind of what's termed by Zurek the decoherence program and things like objective collapse theories. Objective collapse theories don't postulate openness because of interactions between a quantum system and what surrounds them. They postulate that the fundamental evolution equations are non-unitary. And so it's not because of any interaction between some system. You could have a perfectly isolated system and it would still have non-unitary dynamics with an objective collapse system. Formalism.
Yeah. So just one also slight question is it possible to kind of from like open system models, can you kind of show that you can get these kind of stochastic collapse models from, like, for example, if you had like a GKSL master equation, can you show that you can kind of get similar type of stochastic behavior?
I think I don't know for sure because I haven't been through it, but I think a Brownian oscillator type of model would probably ends up giving you something that looks a bit like a collapse model in the position basis.
Okay, thanks.
You'd have to choose very particular microscopics in order to get the rates to scale in the way that they do in GRW, though.
Yeah, so I have a kind of related question or comment. I don't know. So in this collapse model, so either with non-linearity or either if you really understand it as an open system, what you obtain then is as a measurement of your result is statistical mixture of all the results. And so one criticism which is often made is that you get that you obtain that really you have a statistical mixture, but you don't really get that you have a given answer.
Yeah, so I'm going to talk about that in the context of decoherence now, but that certainly is the case, that it doesn't tell us why particular outcomes are achieved on any particular experimental run. Although I suppose one thing you could think about is unraveling these master equations, and then on every run of the master equation, you do get a particular outcome, for example, if it's a quantum jump type master equation.
That was my next comment. But these haven't been really I don't know, written down, I guess.
I think in the objective collapse theories, that's one of the notions of the stochasticity, if I can say it. That in the end, that's what leads on individual runs of an experiment of seeing a particular measurement outcome.
Because then, in my sense, at least, I would say this is a decent explanation of the measurement problem. But maybe maybe we can discuss more later.
I'd have to think about it a bit more. Certainly there are criticisms as well that particularly with decoherence, we'll talk about that in a moment, that it doesn't solve the problem of outcomes. Barry was there.
I just mentioned some work here, which initially I did with Ian Percival. I don't know if you're familiar with his.
Yeah, I've read his Quantum Jumps book.
You read his book?
Yeah.
So he originally worked on this quantum state diffusion.
Yeah, quantum state diffusion.
It's a stochastic model. Absolutely everything is perfectly kosher about it when you frame it in terms of a model of sort of heterodyne measurement process, continuous measurement process. And that fits everything in terms of a kind of continuous unraveling of a master equation or something like that. But he also did a follow-up work, which was this thing called primary state diffusion.
Okay, I'm not
was-
aware of that.
The book is called Primary State
Right.
Diffusion. Maybe there was another book as well, but anyway, the primary state diffusion was getting deeper into this collapse problem with the similar stochastic model. But I wondered if you knew about that and where it fits into all this.
Yeah.
I didn't work with him on the primary state diffusion. That was a different direction that I didn't want to go in. But you know, in my mind, it's a sort of development of the quantum state diffusion that we had worked on together.
So I've read his quantum state diffusion book that's just called Quantum State Diffusion.
All right.
I haven't read or even heard of the primary state diffusion one actually. So it sounds like it'd be interesting to look at. But yeah, no, I can't comment on that, I'm afraid. I was reading it and using it for modeling noise in quantum computers.
Sure.
Years ago, actually, before I even did my PhD, as part of a placement at Hewlett Packard, when they used to have a quantum computing research group that they don't have now. They got rid of it.
With Tim Spiller, maybe?
Yeah, with Tim. Tim was supervising. They decided to concentrate on printers instead. Okay, were there any other questions? If not, we'll go on. Well, it brings us on well to this discussion of the density matrix and decoherence. So I'm not going to present things within a stochastic formalism, but actually within the density matrix formalism. So, I mean, let's go through a little bit of recap on pure states, mixed states, and the density matrix, and then we'll have a bit of a look at decoherence processes and how they fit into a measurement problem. So apologies if I'm telling you everything that you know already, but it's always nice to be told things that you know. So we're used to dealing with closed quantum systems, at least when I give these lectures in Manchester. Most of the students in the course have not seen notion of mixed states or density matrices before, so that they're used to dealing with closed quantum systems. That means you have complete knowledge of the state, and that means you can represent it as a pure state. For example, some superposition between spin up and spin down with some coefficients, complex coefficients alpha and beta. And then the spins are in some basis that we represent by these column vectors here, 1, 0, and 0, 1, if we want to write it explicitly in terms of a vector that then becomes alpha and beta. If we want to define a projector onto that pure state, remember the projector is defined as this outer product. Then we take this product as alpha and beta with the row vector, the conjugate transpose. So we have alpha star and beta star, and then that gives us this 2 by 2 matrix where the diagonals, termed the populations, give us the probability of measurement outcomes for either of the basis states, so 1, 0 or 0, 1, and the off diagonals encode the coherences inherent within the superposition. Okay, so, well, I've said what's the first bullet point there already. Expectation values of within the density matrix formalism obtained by tracing with projectors onto the observable. So, for example, if I want to know what the expectation value is of getting spin up, then I construct that projector within the within our current representation. That matrix looks just like 1, 0, 0, 0. If I multiply the matrices out and then take the trace, I get mod alpha squared, which obviously is the correct expectation value for getting spin up for that particular state. More generally, for any observable represented by an operator A, the expectation value for within a pure state can be written as the trace of that operator A with the density operator that represents that state. We're just talking about pure states for the moment, but we're going to generalize beyond pure states to mixed states in a second. Okay, so for pure states, working with the density matrix is just equivalent to working with the state vector, essentially. But what about situations where our information is not complete? So, for example, let's say I'm given a state that is a statistical mixture. So say I prepare a state and I give it to you and I tell you there's 50% probability I prepared that in spin up and 50% probability that I prepared it in spin down, but I don't tell you which of the states I gave you. That's one particular type of mixed state, and we need to know how to represent that. And it's not clear how one could represent it with a pure state, and that's because it's not possible to represent it with a pure state. You could also have incomplete information for other reasons. For example, due to uncontrolled interactions of a system with our surrounding environment, whose degrees of freedom we can't track. You could also have incomplete information if you have only one particle from an entangled pair and you're only able to probe a particular particle from that pair, for example, then you wouldn't be able to reconstruct the full entangled state. So in these situations, we need to consider mixed states that don't then have a vector representation. And note that these kind of mixed states actually are subtly different. The first one where I give you a state that's prepared with some probability in either spin up or spin down is known as a proper mixture. Then we know that the actual state is either spin up or spin down. We just don't know which one it is. The second case is termed an improper mixture. There, the mixed state tells us about outcomes of observables when we make measurements, but there's no way to actually say, well, I have this given pure state, I just don't know which one it is. There is no notion of a pure state for that system anymore. If I have, for example, an entangled pair, I can't represent one of that pair by a pure state. It will never be possible to represent it in such a way. And so I don't have an underlying state that I can say I have with probability, 50-50, for example. And it's important to distinguish these two cases rather than always thinking that there is some underlying ensemble of pure states. That is not the case for improper mixtures. Okay. Let's consider a proper mixture, though, because it's a bit simpler to think about. So we consider a state that does have an underlying pure state, but it's prepared with 50% probability in spin up and 50% probability in spin down. So we don't know what it is because for some reason I'm being awkward and I'm giving you that state with some probability, and I'm not giving you the full information about it. So it's not a superposition state of the form 1 over root 2 up plus down. There are a number of ways to see that. One is that there's no superposition in the underlying ensemble here. So this is a proper mixture, so the ensemble does actually exist. Also, you could do measurements in different bases on a mixture of states, a statistical mixture of states, and on a superposition state, and you would find different measurement outcomes. And so the superposition state is not the correct way to represent it. One way to motivate how to represent it is to consider the expectation values of observables, however. So let's consider the expectation value of some observable A. We would write that, because we have a statistical mixture, as half times the expectation value that it's in the upspin state and plus half time the expectation value that it's in the spin down state. And remember from our discussion on the previous slide, that's half times the trace of A with the projector onto the up state plus half times the trace of A with the projector onto the down state, which we can write as trace of A rho as before. now we have a definition of a density matrix for this particular mixed state. It's given by 1/2 times the projector onto spin up plus 1/2 times the projector onto spin down. So we can see now that it's a diagonal matrix with probability 1/2 along the diagonals. So it gives us the right statistics for measurements, but there's no off diagonal elements. So there's no coherence present. And I couldn't represent that as a standard ket, you know, as a column vector. So the density matrix can then describe both pure states and mixed states. So it's a generalization of the state of a quantum system to include situations where we have incomplete information. And that could be, as I said, because we either don't know the preparation of the state, for example, or because we only have access to a subset of the particles that constitute the state. And in essence, we have to trace out those that we have no knowledge about. This is then giving us a reduced density matrix, as we've heard, particularly in Marco's lectures, that gives us then a mixed state representation. In general, we can write a mixed state in any basis we want by summing over the amplitudes or the coefficients that give us how each of these projectors build up that density matrix in some given basis, and the time evolution is given by the von Neumann equation. So how does decoherence come into play then? We're going to consider a phenomenological approach because it's simpler for the discussions on measurement. But obviously, we could look at a microscopic model as well, and we've already seen a number of microscopic open systems models. So imagine that we have a system that's prepared in a superposition, as we did before when we were talking about ideal quantum measurements, and that subsequently interacts with a large macroscopic environment. So typically, we have no way of keeping track of the environmental state, and that is represented mathematically by taking the partial trace over the environmental degrees of freedom. And generically, this leads to decoherence, which is the loss of coherence of our system. Usually we find that we get some kind of reduction, for example, of the off-diagonal elements of the density matrix. They could go to 0, they could go to something else. Of course, other possibilities can happen. You know, we can easily change the probabilities as well by, you know, something like a spontaneous emission process. But let's consider processes that just give rise to loss of coherence for now, not variations in the probabilities of the actual measurement outcomes. So a little bit more specifically, let's consider some system in a superposition at the top line there, and the environment in some initial state epsilon 0. And over time, that superposition evolves so that the environment becomes entangled with the superposition state, where we've got an environment state that is in the up state, or we represent by epsilon subscript up associated with the upspin state, and an environment state that's represented by epsilon subscript down for the down state. The density operator for this, well, you can calculate it, and it can be represented in this way. So we see that we still have population terms, but now they include the degrees of freedom of both the original system and the environment, and then coherence terms as well, that now are also including environmental parts. So if we assume we can only probe the system, as I said, we then trace over the unknown environmental degrees of freedom. And you can think of that a bit like as an analogy in probability theory, where you find the marginal probability distribution by averaging over variables that you're not interested in. And that gives rise to a reduced density matrix. And the reduced density matrix, then we take the diagonal elements with respect to the environmental states. So that's the trace over the environmental states, and that picks out only our population matrix elements, and so we end up with this diagonal matrix. Now here I've assumed that in order for the environmental states to disappear in this trace, the off-diagonal states, that the epsilon subscript up and epsilon subscript down must be orthogonal. Now, obviously, that's not always going to be the case, but if we consider that a generic environmental state, for example, what have I called it? I called it epsilon, didn't I? Epsilon up is some product over some large number of particles n of individual states. Let's call them E up subscript I, and then epsilon down is some product E down I. Then even if the overlap of individual environmental states, E up, E down, I, for each I is close to 1. Remember, it can't be larger than 1. It can be smaller than 1, but it can be close to 1. If I product enough of these things, eventually I'll get a product of the macroscopic state that's very close to 0. And so even if each interaction between the system and the environment is only giving rise to a small amount of information leaking into the environment, such that these overlaps become suppressed, but only a small amount suppressed. If I take, enough of these and product them all together, a number close to 1 to the power 100 is much, much smaller than 1. So we end up with something that ends up being very close to 0. So generically, large environments, by performing scattering, for example, off the system, taking away a little bit of information about the system, end up giving us the destruction of the off-diagonal elements of the system. Now, of course, microscopically, one can come up with models where this behavior is apparent as well. And as I said, usually for more realistic microscopic models, the behavior is more complicated than this, but this is a simple example of a decoherence process. This is a pure decoherence process, as it's sometimes termed. It only changes the off-diagonal elements of the density operator. Yeah.
Can you say something about, I mean, any density matrix is always diagonal in some basis,
Yes.
in its own basis. So here you define decoherence as a process where the off-diagonals disappear.
Yeah.
So it's basis dependent, right?
Yeah.
So,
yeah.
So in which basis does this happen?
So one has to appeal, actually we'll come on to this at the moment. So in terms of measurement, one always has to define what basis one wants to measure in. And so there's an operational definition of, like, I want to try and measure in this basis or that basis, which gives why our basis states in the original case are meaningful. But also, microscopically, a system and environment might interact through a particular degree of freedom, and then that would give rise to a natural representation in one basis or another.
So I just wanted to find out, so such density matrix where the off-diagonal elements are 0, can we call that density matrix a classical density matrix, or?
I mean, it's essentially classical. I suppose it has no quantum coherences associated with it in that basis.
Okay, so because yesterday I was having an issue with the H bar going to 0, we call that what you call a classical
Yeah.
limit. So if one can be able to throw away the off diagonals, then we can use that as a classical limit.
Yeah, there are so many different classical limits of quantum mechanics that don't all seem consistent with each other necessarily, that I don't really know how to define the classical limits of quantum mechanics in terms of a single definition, if you see what I mean. And the definition often depends on, or at least to me, the definition often depends on the particular system or understudy or the question one is asking about that system. Here, I think it would be relevant to consider something. So this is just a picture in position space of the off-diagonal elements of the density matrix in that space decaying over time, just as a pictorial representation. I guess it would be fine to think of that diagonal matrix element, diagonal matrix as representing some kind of classical state that's been produced via decoherence. And that would be the interpretation in terms of measurements as well. So how does this come into measurement? So let's consider the ideal measurement scheme again, but now we're going to augment it by an environment that's inherent to the apparatus. So the apparatus is some big macroscopic system, and we're going to say that that big macroscopic system interacts with some environment that surrounds it. So it could just be, particles scattering off it. It could be electromagnetic radiation. It could be neutrinos. It could be anything. So this is macroscopic. So again, remember our ideal measurement scheme. We had some spin prepared in some particular state. That state was a superposition of spin up and spin down, where I've given it in the Z basis. The apparatus is in the ready state, and the environment is in some initial state epsilon0, and then after some time, this superposition gets mapped, so enlarged onto the apparatus state and the environmental states that are appropriate for those apparatus states. So it's completely analogous to our previous ideal measurement example, except now we've got these environmental states as well. If we do the same thing of tracing over the environment, we see that as long as these two environment states become orthogonal or close to orthogonal on some time scale, then we end up again with only the diagonal matrix elements. And so decoherence has kind of collapsed the state into a mixture of the two possible outcomes. So at the very least, coherence terms are no longer present within the description. So it's giving us a hint as how decoherence could tell us that we should only get outcomes that are, in this case, spin up or spin down. Well, we're not getting outcomes that are superposition states. So the idea is that the inclusion of an environment, which is generally considered, unavoidable, we can't isolate a system completely from any environmental influences, has then given a physical argument for collapse. And it's also possible to provide a preferred basis, although one has to go more to microscopics in order to do this. But as you said, by a particular form of detector environment interaction, Hamiltonian. So of course, if I have some system and some apparatus that has an environment inherent to it, the system and apparatus plus environment will couple together in a particular manner. And then that can set, that coupling term can then set a particular basis within which the apparatus performs measurements. Notice that the density matrix approach itself doesn't explain why specific measurements should be given, should give a particular outcome. So it tells us about probabilities of getting outcomes, but it doesn't tell us why, when we perform an experiment, we get one outcome or the other. As we said, possibly going to individual trajectories could do that. We would still be left with the problem of why anything is probabilistic in the first place. Okay, so we've introduced mixed states about which we don't have complete knowledge, and then they're represented by density operators or density matrices in the matrix representation. And we showed that tracing out unknown environmental degrees of freedom can remove coherence terms within a simple model that leads to a physical mechanism for collapse in a measurement process, but it doesn't tell us why we get one particular outcome or another on any given run of an experiment. I think probably given the time, I won't go on to objective collapse theories in many worlds, but I didn't have anything particularly profound to say about them anyway. So I'll probably finish there.
So I just wanted to ask about the measurement problem. Is it still a problem for our generation? Because I've heard people talking about what you call that you can actually make a measurement without destroying a photon. I think I've heard from Haroch, they call it quantum non-demolition, something.
There is such a process of quantum non-demolition measurements as well. It's a different way of performing measurements, so it's not quite in the same setup as we're considering here. That doesn't remove the need to understand what happens in projective measurements, but it is another way of probing quantum systems that's very interesting and useful in its own right. So yes, it is still a problem for our generation, if you want to put it that way. Although I'm not sure I'm same generation as you or not. I might be much older than you are. I think there was one behind you first.
Yeah, maybe mine will be quick. Just so I thought trace was basis independent. Yeah, just there's something I'm missing there, because if you form the partial trace, then in some basis the coherences decay, but shouldn't the partial trace be basis independent?
Partial trace. Yeah, I can perform it over any orthonormal states of the environment, I think. Yeah. I don't think I will end up with different conclusions.
Not all states of the environment necessarily. If you're not in a preferred basis, then this environmental states won't be orthonormal.
No, but the combinations will add up such that they give me the same matrix back out again, I think.
Okay.
I thought Camille had.
Sorry. Yeah, no, maybe it was more common if you, can come back maybe on the previous slide, or
Look, this one.
Yeah, one.
That one.
Yeah, that one. Yeah. So yeah, I mean, again, as we already commented, this final density operator here, it's a mixture, and yeah, it doesn't really explain why, when we do an experiment, we end up with a definite answer. But I think this also depends how you interpret this mixed state. Meaning, do you really think this is a state of the quantum system, or do you think actually my quantum system is in one of these pure state with a given probability? But yeah, so
No,
I guess
yeah, no, this is most definitely an improper mixture. So the actual state is this state given at the top here. So there is no notion of an underlying pure state for the spin. It's impossible for me to say that. So that's the initial state. Obviously,
Yeah.
decoherence occurs, and then I
Uh-huh.
get this state. But it's not possible for me to then say that the spin is definitely in one state or another just with some probability. The act of tracing over the environment has just removed information and given us a mixed state description. So it's definitely an improper mixture in this situation. So I shouldn't, I mean, this is there's a number of reasons why, although looking at the unravelings is attractive in terms of jumps or quantum state diffusion, we do have to be careful. One, we have to be careful about what we interpret those states as representing, whether they represent real states of the system or not.
Yeah.
And that's dubious given the improper mixture interpretation. Also, even if we can interpret them, we're still left with the problem of why on one particular run you get spin up and then on another particular run, which has no difference to the previous run, you get spin down. So where the stochasticity comes from.
Yeah.
I mean, these are really interesting questions.
Yeah.
I don't have any answers. Was there another question?
So the question was really more about what is your view of the multiverse approach, which got skipped off at the end.
Oh, yeah.
And the point being that the multiverse thing is very popular in you know the world of non-physicists and in filmmakers and so on, and it gets a lot of attention. And I'll just quickly give you my view, which is that in its most naive form, where you have this continual splitting of universes, well, never minding that it's unsatisfactory because it's so wasteful somehow, and you don't seem to find that physics is wasteful, but it could be, so never mind that. The real problem is that in the naive form, it's not something that's testable. Maybe you will contradict me on this, and I hope I get a chance to finish what I'm saying. But and if it's not testable, then I think it's not science, and so this is non-science, or even nonsense. But I think I have heard at some point that there are versions of the multiverse where there can be some interactions between the splittings, and that would make it potentially, possibly testable. And I think somebody was telling me that, but do you know any more about that? Can you comment?
So, yeah, I didn't get onto it, but actually I didn't, like I said, I didn't really have that much to say about it. So if, I mean, basically it was just a bit of a historical outline about many worlds, and maybe I can't remember what else I was going to say. You know, a very basic description of it. So that's just to say you didn't miss anything important by the fact that I didn't get onto it. It's essentially copied from a Wikipedia article or something like that. I mean, it's not as bad as that, but you know, you'd get as much from a Wikipedia article as you would from this. Yeah, so there's a couple of interesting things about many worlds, I think. I mean, in the naive form, as you say, I entirely agree with what you say, and I'm not particularly a many worlds enthusiast, but So David Deutsch, for example, claims that already there's evidence for many worlds because every time we see interference in an experiment, that is many different worlds interfering with each other. I mean, I don't see a more underlying reason to believe that that's evidence for many worlds beyond any other interpretation. But he has made statements along those lines. Hopefully, I'm not misrepresenting them. There's some very interesting work that I've not had time to go through in detail recently by Philip Strasberg in Spain, who's been trying to simulate look at the kind of dynamics of many world situations to see how preferred properties might emerge if we allow these branchings of different worlds from each other. And I don't want to say much about that because I've not had time to read those papers. They're recent papers. But I would encourage you to look at them if you're interested, because I'm certainly going to read through them to see what they have to say. But he's trying, I'm not sure whether he's a many worlds enthusiast himself, but he's trying to explore it in a more quantitative manner. Any, I don't know how we're doing for time. Yeah.